Hello everyone, welcome to Scale 2025. My name is Zhenyu. Today I'm going to talk about from silicon to scale at AMD. Let's get started. So today we're seeing that supercluster computing are getting bigger and bigger. The top 500 supercluster, 5 of the top 10 are from AMD. And both number 1 and number 2 are supported by AMD. It's all X-flop supercomputer cluster. And we also are very careful about the grain energy. So top 500 grain, 15 of the top 25 are from AMD as well. We're not only looking to scale big, we are also looking to scale more efficient. So how to scale efficient? Our answer is to do hardware-software co-optimization. So we can see if we only pile up all the hardwares, you will get very low utilization and low stability. And if we do full stack software optimization, including using the extra parallel strategy, kernel level optimization, and other key technology like the high-speed storage file system, etc., we will get a full utilization of the GPU cluster and with higher stability. And AMD has the full software stack to support your needs. It's starting from the high performance math library, like the ROCm libraries, and also to the compiler tools we help you to compile, debug, and profile. We also provide cluster level monitoring and other resource orchestration tools. AMD not only supporting all those software tools, we also have a deep collaboration with our open source community. From Hugging Face, we support 1 million plus model with the open box experience. At the framework level, we work with PyTorch and other vendors to provide day zero support. We also do a lot of CI/CD regressions on those large clusters. In addition, we also work with the Triton, which is well-known kernel level optimization tools to help our community to keep growing. There are other lot of open source community we are working with, like the VLM, SGLong for inference, JAX, and Onyx for framework level collaboration as well. Okay, let's get started with more case study here. The first one is the large language model training, and the second one is the climate weather modeling. The third one is the material science exploration with foundation models. And climate weather modeling got the Golden Bell finalist. The first case is about efficient scaling for language model training. And as we know, large language model training, it's need a lot of compute resources. For 1 trillion parameter large language model, it's more like ChatGPT scale models. Frontier, we can use only 3,000 GPU to get a similar performance. And also, it's fully supported by AMD X-Scale AI capabilities on ROCm-based software stack. The key technology to support all those scalability and efficiency are including 3D parallel strategies and efficient communication with ROCm libraries, mixed precision training, as well as hardware agnostic scalable training pipeline, which help to make this cluster more stable. We saw we have achieved very strong 100% weak scaling efficiency on the supercluster. And for large model like 175 billion and 1 trillion model, we get up to 89% of strong scaling. Next, let's look at the Orbit, one of the efficient multimodality scaling example for AI science. So as we know, global warming make the weather prediction more and more important for our daily life. And the challenge for this one is we have to use 3 petabyte multimodal dataset to do large-scale training. And the data resources are from different format, and also it uses a lot of different type of data. For example, they are using the temperature data, ocean current data, and also soil, sea ice, all kinds of data together. So it's about 100 plus type of the physical variables here. And also we use 3D spatial grids as the data structure and a bunch of other requirements for this case. So how to make an efficient scaling on this huge number of data and large parameter models? What we do here is to do parallelism strategy called hybrid stop. It's hybrid scalable tensor data orthogonal parallelism. Here we use tensor parallelism to split the model layers, especially the attention heads across GPU for larger layer compute. And we use pipeline parallelisms to slice the model into sequential stage to enable deep network training. And for data parallelism, we process multiple training samples in parallel. And most important, we're using spatial parallelism as the fourth dimension, that we can do data decomposition on top of geographic physics data, which we can split across spatial grid dimension. And next, let's see how we do with all those very sophisticated parallelism technology. So with this, we can scale up to 113 billion model parameters with 91 weather climate variables. It's the largest dense vision transformer model by the date to publish, and also it has been 200x larger than the largest climate AI model. The model uses 1.6 exaflops on 49,000 GPUs. It's the first model that run on exaflop for vision transformer model, and it's achieved very high accuracy than other method for long-term forecasting. In addition, it's also very energy efficient. It only needs it can do a real in-time model inference prediction on only a few GPUs. Next, let's go to another type of application. It needs to do efficient graph neural network scaling. The domain is about material science, especially for new material structural exploration. We are facing three challenges here. The first one is large number of data. We are facing 100 million of the data here. The second one is we are doing multitask learning at the same time, which means you not only take care of the global property like the energy, you are also looking into the local property like the force. The third one is that we are also looking to do a mechanism for uncertainty qualification, which is very important. When we provide the prediction, we also give the confidence of the estimates. So the top challenge here to scale graph neural network efficiently is how to set up huge number of hyperparameters. Here we have 400 unique hyperparameters from the structure of the graph neural network to the training parameters and other hyperparameters together. So what we do here is we do a hyperparameter optimization technique, which help us to find the top 20 most accurate and energy efficient graph neural network configurations. And by using that, we can scale up to 90% of the whole cluster and get the most accurate top 20 solutions. So let's make a summary. So the key technology here we're using is, first, we're using the multi-head GN neural network architecture under distributed PyTorch framework. And second, we're doing multitask learning, not only on the node level, but also on the graph level to give a global view. Also, we are doing early stop and example the previous graph foundation models. Therefore, we don't need to run from scratch. And last, but also very important, is that we integrate with the distributed data store mechanism where it can do fast distributed data loading, since we are taking care of 100 million graphs together. So by using all those key techniques, we can scale efficiently. Scale up to 90% of the supercluster, about 16,000 GPUs, and it shows very linear, strong scaling, optimized both for accuracy and computation cost. It's also very big for the community because it's all open sourced. And by using that, you can dramatically reduce the time of the discovery from years to days, even to minutes. Okay, so we are done with the case study. As we are scaling even bigger and bigger, what's the next most important bottleneck? I would say it's the collective communication bottleneck. So from this table and charts, we can find that for different type of workload, once you're scaling even bigger, you get even larger portion of the collective communication, from language model to recommendation model. How can we handle this? So one of the solutions is to do fine-grained communication and computation overlap, which means we put the communication and computation kernel into one fused kernel. And in one fused kernel, some of the work group are doing computing while others are doing communication. And it's sending data as soon as the output fragment is ready. So we'll reduce the gap between the communication and computation. So our results shows that for distributed recommendation model and the intro and internode hardware, on average, we see up to 31% reduction in execution time. All right, so let's summarize here. Today, we're not only looking for scaling big. Actually, the future of AI is not only for scaling big. It's also about scaling across different application domain efficiently. What's the solution here? I would say we need to do more domain-specific hardware software co-design to achieve the best efficiency. And at AMD today, we're working on towards a even highly efficient and reliable training system by putting every pieces together, not only taking care of the training efficiency, but also taking care of the end-to-end training stability, as well as integrate all other observability, telemetry, scheduling system, and even the end-to-end pipelining of the training process into the software stack. Thank you for listening to this talk.